All right, good morning, everyone. So today we'll finish our conversation first about the Young's double slit experiment. So again, I talked about this last time. So this was, again, the experiment that definitively showed that light was actually a wave, counter to what other people had thought. And of course, then we jump forward about 20 years, and then we show it's actually both of these two things simultaneously, but let's not worry too much about that. But again, what's happening here is I'm sending coherent light, something like a laser beam would work just fine. So I mentioned this kind of last time, but very briefly, this wouldn't work for something like sunlight. So I couldn't shine sunlight on here and expect to see light spots and dark spots, things like that. And the reason for that is that sunlight is not what we call coherent. Coherent basically just means that it maintains the same frequency at pretty much the entire time, but white light is a superposition of basically all possible frequencies. So the coherence isn't there, so you can actually do this with white light. So sunlight, you have to do this with something that is monochromatic and something which has a lot of coherence to it. So something like again, a laser beam would work just fine. So here we're sending then plane waves onto these two slits. Each one of these slits has a width of A, but separated by a distance of D. Here we then get diffraction. That diffraction then causes spherical waves to come out through, and then we're getting interference between those two waves. And then what we're seeing is then bright spots and dark spots on the screen out here. If I drew those out here, I'm gonna get some sort of central maximum, and that's something like this, and a dark spot. And we're gonna get bright spots, which kind of decay as I go further and further away. So I'm gonna get things that look like this, okay? So here we can talk about the locations of the bright spots and dark spots using the path length difference that we talked about 100,000 years ago. All those beautiful things. So this says then that since D, capital D, which is the distance from the slits to the screen, is much, much bigger than the separation distance between the two slits, then in that case, this path length here is approximately the same as this one, except for this little tiny piece here. So if we find this angle here, which is the same as this angle, which is the same as this angle, since these two lines are approximately equal to parallel, then here, the path length difference is simply just equal to that distance D between the slits times sine angle between the two, which is either equal to n lambda for constructive interference. So this is when we have a bright spot. Or this guy, n plus a half, which is when we have a dark spot. So this is our Young's double slit experiment. One thing we can see here is that since this angle here is the same as this angle here, which is approximately the same as this angle here, again, assuming that D is much, much bigger than little d, then theta here not only defines this angle here, but it also defines the location of all of these different bright spots and dark spots. So what I mean by that is, if that up there was the nth bright spot, then this angle here, theta, which we can call theta n, then tells me the angle at which this is going to be relative to the horizontal. So just doing a little bit of trig, actually nothing too bad. We can then find the angular dependence for constructive interference occurs then at the inverse sine of n, which is the nth harmonic here, times the wavelength divided by d, and then the location, angular location then of the nth dark spot is then the inverse sine of 2n plus 1 times the wavelength divided by 2d. So these are their angular locations. So let's use this. Let's do a problem. So go back. There's my Young's double slit. So let's look at this chapter. Problem 2, I think. Oh, problem number 1. Good. So this says, at what vertical positions does the nth maximum occur? And then what is the separation between successive maxima? So let's take a look at this. So what this is asking then is, if I go back to my picture, I want to know at what height above here does this nth occur? So I want to know if this is my nth maximum, what position is this guy at? So let's call that guy y of n. So where does that guy actually exist? So how high above the central maximum here would I find this guy? So let's call that the y-axis, and let's call that position y sub n. So let's kind of redraw our picture here. Nice and pretty. guy, and this guy, and this guy. That's path 1, path 2. And then what I want to know is, what is this distance here? So what is y sub n? What's this guy? So what do we know? So we know is that what? D sine of theta n, right, because this has a theta n component to it as well, is then equal to, because this is constructive, we need this equal to n times lambda. Now here, we're working on the assumption, again, that D is much, much bigger than D, which means then that what? Our angle here is going to be something ridiculously small. So if this distance here is much, much bigger than this distance here, the angle at which this thing is going to be lifted up is going to be a ridiculously tiny angle. Which means that since D is much, much bigger than D, what this means then is that theta n is going to be much, much less than pi over 2. Okay with this? So if that's true, what that means then is what? Sine of theta n is approximately just equal to tangent of theta n. Okay with this? Let's write it out. So tangent of theta n is then equal to sine of theta n divided by cosine of theta n. But if theta n is much, much less than pi over 2, i.e. if theta n is around 0, then what? Cosine of theta n is approximately equal to 1. So this thing is approximately then just equal to sine of theta n divided by 1, which is then just equal to sine of theta n. Everyone okay with this? Calc tours in here. Are you doing Taylor and Maclaurin series and all that kind of good stuff at this stage? You've seen this by now. So this comes from the fact that what? For sine of theta n, this is approximately equal to what? Theta n minus theta n cubed divided by 3 factorial plus blah, blah, blah. Cosine of theta n is approximately equal to 1 minus theta n squared divided by 2 factorial plus blah, blah, blah. Okay. So basically, as long as theta n is small, first order term for this guy is simply 1, and then this guy is simply sine of theta. So what that means then is we could use the geometry, hence the tangent here, to replace sine of theta n with simply tangent of theta n. So I can then write d tangent of theta n then is equal to n lambda. Now, why do I care about that? Well, I care about that because according to this angle here, the opposite sine is simply equal to lambda or yn, and the adjacent sine is simply equal to d. So this becomes d times yn divided by capital D then is equal to n times lambda. So from this, what this tells me then is that what? The position of the nth maximum is then simply equal to what? N times lambda times capital D divided by little d. So this is my location. So location yn is then equal to n lambda capital D divided by little d. So this is my location of the nth maximum. Okay? The next thing I want to know is, well, what's the difference then, or the distance between two successive maximum? So what does that mean? So the difference between two successive maximum, let's call that delta y, is then going to be equal to yn plus 1 minus yn. Right? This is going to be the difference or the distance between two successive maximum. So using what we just wrote down, that's going to be n plus 1, right, times lambda times d divided by d minus then n times lambda times d divided by d. Multiplying all this out, this becomes n times lambda times d divided by d plus lambda d divided by d minus n lambda d divided by d. Well, what happens to the first term and the last term? They're going to cancel, okay, which means there is no n dependence. So this is simply going to be equal to lambda d divided by d. So what this tells me then, which is something which is kind of interesting, the spacing between the maximum is actually a fixed constant. every maximum is separated from each other by simply lambda d divided by d. So if I went back to my beautiful picture, so if this was the nth maximum here, then this location here is going to be the n minus 1 maximum, which means the distance between these two maxima is simply equal to lambda d divided by d. So all consecutive maxima are all spaced out by exactly the same distance. That distance is simply the wavelength times the distance from the slits to the screen divided by the distance between the two slits. If I did the same thing for the minimum or the locations of the dark spots, I would find something similar as well. Those are all also spaced out by exactly the same amount of distance. So it's kind of interesting. So it would seem that it actually depends on n, but it turns out it doesn't depend on n. They're all fixed equal distance away from each other. No matter which nth I'm looking at, it's separated from the previous one and the one before that by exactly the same distance. So this is our Young's double slit experiment. Okay? 1, 2. So good. We've had enough of Young. We can move on to something else now. So, moving away from Young, we're now going to start looking at more wave properties. And again, what we know is whenever a wave encounters a boundary, one of two things is going to happen. So let's say here's our boundary. Here's our boundary B. I originally wrote it as a D and tried to turn it into a B, and that didn't work, so let's write it actually as a B. So this is our boundary. So what that means then is we have a wave, in this case light, which is moving in medium 1, and then going to go to some other medium 2. So this is our boundary between the two mediums. So whenever I encounter some sort of boundary, one of two things are going to happen. So let's say my initial wave is coming in like this. This is my initial wave, and this thing is coming in at some angle relative to the vertical. So let's call that theta 1 for theta initial. Well, we know part of the wave is going to be reflected. So part of the wave is going to be reflected off in this direction. So this is going to be sent off at some angle theta r, which is theta reflection. And then the other part is going to be transmitted through the medium and then come out something like this, and this guy's going to go at some other angle theta 2. So let's talk about each one of these guys. So the first one, let's talk about when it happens on reflection. The law of reflection says that the two angles, theta 1 is actually equal to theta r. So what this says then is that the angle of incidence is equal to the angle of reflection. This is my incident angle is then equal to the angle of reflection. So this will always be true regardless of the shape of whatever it is that I'm reflecting off of. So for example, here I drew a nice flat straight line, hopefully. From my perspective, it looks like a nice flat straight line. But if this thing was rounded, for example, if it did something like this would also still be true. So here, if my incoming wave hits here and then gets reflected off in this direction, again, if I draw my normal inside of here, this angle theta incidence is still equal to the angle of reflection. Okay? So basically what happens is even though this is curved and a small distance around here, this is locally flat. Same thing as the Earth. The Earth is curved, but when we stand outside, what we see is locally flat ground. So as long as this area here is small enough, this will be locally flat. So this always is going to abide by the law of reflections. So that's it. That's all the law of reflection says. So anytime I have an incoming light hit something, bounces back into the same medium, the angle of reflection is simply equal to the angle of incidence. That's it. So let's do an example. So this example says that we have two mirrors. So here's mirror 1 and here's mirror 2, which are set up to each other so they are perpendicular to each other. So here's one mirror here, here's a second mirror here. Now what we're going to do is send in light so that my initial angle of light is going to come in at an angle of theta 1, which is equal to 15 degrees. That light then is going to reflect. So part of it's going to reflect hit this mirror here, and then this portion is going to reflect off in this direction. And what I want to know here is, what is this angle here? So what is this final angle? So let's call that theta final. So what is the angle at which this guy reflects off relative to the, in this case, vertical or horizontal? Okay, not too bad. So good, so let's apply our law of reflections. So the law of reflection says that what? My incident angle is coming in here, so that makes an angle with the vertical, which is this angle here, which in this case is what? 75 degrees. Right? So my law of reflections then says, well, my reflected wave then, which goes off in this direction, gets reflected off at exactly the same angle at which this one was incident at, which means that this angle on this side must also be equal to 75 degrees. Okay? So this is my law of reflections. Since that's 75 degrees, we also know that this angle on here is 15 degrees. So let's go ahead and write that one in too. So this one must also be 15 degrees. Okay? Now, this light, which is coming in this direction, then is going to reflect here. So we need to know now this angle, which is now the angle of incidence. But since this is a parallel line, this is a parallel line, this is a bisector, this angle here must be equal to this angle here by geometry, which means this angle here must also be equal to 15 degrees. So my law of reflections then says, well, since this is coming in at 15 degrees, this one has to be reflected off also at 15 degrees. So we know that this angle here must also be 15 degrees. And since this is the right angle here, because I'm always talking about a normal, so this is 15, this must then be 75. So my angle final is then equal to simply 75 degrees. Okay. Law of reflections. Nice and simple. We had enough of that. So let's go back to our picture. So now we know how to deal with the reflected part. Right? In this case, the reflected wave comes back into medium 1 from medium 1. But the more interesting question is, what happens when it goes from medium 1 into medium 2? What happens here? So this we already talked about before when it came to lab number 10. But let's kind of talk about it again. So what happens here depends on what's known as the index of refraction. So let's talk about the index of refraction first. So what's the index of refraction? Well, the index of refraction is whenever light travels in some sort of dielectric material. So if I have a dielectric material, remember dielectric material is just a fancy word for material, for an insulator. What happens is as the light moves inside of that insulator, we're going to then get dipole separations. So on the inside, this thing is going to separate and become a dipole. Say positive charges here. So that here I'm creating these little tiny dipoles. Each one of these dipoles has a dipole moment, but more importantly, it has an electric field. That electric field, we know, points from the positive to the negative, so these are the directions of my electric fields. So what happens then is when the light moves inside of the dielectric, remember the electric field is part of an electromagnetic wave. So electromagnetic wave, i.e. light, has part of an electric field as well as a magnetic field, which are oscillating perpendicular to each other. So what happens then is I get the superposition between the electric field created by the dipole separation inside of the material, plus that of the electric field itself, which overall causes the electric field to reduce, which causes actually the speed at which the light is traveling to actually reduce. So what happens then is the light, which is actually moving on the inside of here, moves at a much slower rate, and the rate at which it moves is equal to the square root of mu divided by epsilon, where mu and epsilon are the permeability and the permittivity of the material itself. So we talked about this kind of before. Epsilon is equal to kappa, which is the dielectric constant times epsilon naught. And then mu is going to be something similar, but this is the permittivity of the material. So basically what happens is we can kind of see from here, epsilon is much bigger than epsilon naught, which means that the speed at which the light is moving is actually much slower. So within it moving inside of the dielectric material, this velocity then is going to be less than that of the speed of light. Another way you can think about this, if you don't really want to think about it as a wave, you can think about it as photons moving, but photons are coupled to charge, which means as the photon is moving through, it feels a force pulling it backwards from the positive and negative charges of this dipole separation. Which means that as the photon is trying to move through it, it basically feels a drag force acting onto it, which means that it acts as if it has acquired a mass. Anything with mass can't travel at the speed of light, so it has to travel slower than the speed of light by definition. Hence special relativity, something you would learn in modern physics if you're going to take that. But either way you want to look at it, what happens is it travels at a much slower rate. So from here, we can define this index of refraction. So the index of refraction, N then, is equal to C divided by V. So the index of refraction is then equal to the speed of light divided by the speed at which this object is moving within inside of the dielectric constant, which means N is always going to be greater than or equal to 1, where the only time it's equal to 1 is when it's in air/vacuum. Technically not even in air. In air, it's actually like 1.001, but we're just going to call it 1. Close enough. For anything else, this thing then has to be greater than 1. Now, one other thing that's kind of interesting about dielectric constants here, or the index of refraction, is that it turns out that this guy is actually frequency dependent. Which basically means that when light, something like light, enters into some sort of dielectric material, each one of the different frequencies at which makes up white light will all travel at a faster or slower rate. They all travel at different rates. Which means what happens is when you shine white light into the dielectric material, you get what's called dispersion. Bless you. Dispersion is when the frequencies separate. So what happens in this case is when the light goes inside of it, each one of the different light rays or frequencies separate from each other, which means you actually see all the different colors. Which leads us to things like rainbows. Rainbows are created by this. So what happens is sunlight, which again is the superposition of all possible frequencies, comes into a water droplet. In that case, once it comes into the water droplet, each one of these different rays bends a different amount because they all have a different index of refraction, because index of refraction is frequency dependent, which means you get dispersion on the inside of the water droplet. So the reds and blues and violets and everything separate from each other. They then hit the back wall, they then reflect at exactly the same angle at which they're coming in, hence law of reflections. At one point, they're going to get reflected, but again, since they're all separated from each other, they're going to recombine at some point, and then split off in the opposite direction. And then once they hit the other side, some of it will reflect it back in this direction, but most of it's going to be transmitted through it, which then gives us what we see as a rainbow. Okay? So for a rainbow to actually work, what has to be true is your back has to be to the sun. So the sun actually behind you, shining into the water droplets in front of you, which is causing then us to see the rainbow. So we see the rainbow arced because basically what it's doing is it's creating a sphere. And what you're then seeing is a two-dimensional slice of that three-dimensional sphere, which causes the rainbow to look like a nice arch. So this is our rainbow. So the reason, again, we see them in certain colors, why we see red on the bottom and say purple on top, or violet on top, is because of this dispersion. Each one of them is traveling at a different rate, causing them to all exit at a different rate, causing each one to be bent differently. So this actually goes to what's known as Fermat's principle. Fermat's principle says that when light travels inside of a dielectric, it will always travel along the path of least time. So whatever path it has to travel to make the time spent inside of the dielectric as minimum as possible. It doesn't want to be inside of it. So it's called Fermat's principle. But again, in general, these guys are going to be frequency dependent. So each one of these is going to feel a different index of refraction, meaning each one is going to be bent differently from the other one. This causes the dispersion. This is also what causes when you shine light into a prism, you can also see the rainbow on the other side. Same exact effect. So this is index of refraction. So how does that build into our story? Well, it turns out that, going back to our beautiful picture, how this thing bends once it comes from one medium to a second medium depends on the index of refraction. So this brings us to what's known as Snell's law. What Snell's law says is, if here is my boundary, here is my incident ray coming in here at some angle θ1 relative to the normal, then the angle at which this one is going to be transmitted at, call that guy θ2, depends then on the index of refractions. So medium 1 has its own index of refraction, N1, medium 2 has its own index of refraction of N2. So what Snell's law says is that N1 times sine of θ1 must then be equal to N2 times sine of θ2. So what does this mean? So what this means is, let's look at the ratio. So we can look at N1 divided by N2 then is equal to sine of θ2 divided by sine of θ1. I think I always talked about this in the video as well, but we'll do it again anyways. So let's look at case 1. So case 1 would be if index of refraction N1 is greater than N2. So in this case, if I'm going from a high index of refraction to a low index of refraction, what happens? Well, if N1 divided by N2, if N1 is bigger than N2, this value here has to be greater than 1. So this guy takes something large divided by something small. This is greater than 1. So how do I actually make this guy then greater than 1? Well, we know sine gets bigger as theta gets bigger, so that means I need this value to be small, this value to be then large, which means what? This means then the opposite. This means that θ2 must be greater than θ1. So what this means is if it goes from something from a high index refraction to a low index refraction, this thing has to bend in such a way that this angle is greater than this angle, which means it's going to bend away from the normal. Okay. So in this case, this would be bending away from the normal. Case number 2, if N2 is greater than N1, well, in this case, this gives me θ1 then must be equal to θ2, or greater than θ2. So if I'm going from a low index refraction to a high index refraction, what happens in this case is it actually gets bent toward the normal. So my light ray gets bent more towards the normal. Now, one consequence of this is we get to see interesting optical effects. And one interesting optical effect we get to see, we get to see cool things like this, like our straw is bent or pointing in the wrong direction. And this is just what is happening inside. So here's a laser shining through a piece so you can actually see the difference in the path. Well, we can actually see all kinds of interesting, cool optical effects because of this. So if you look at somebody in a pool, for example, they may look like they have really tiny, short, stubby legs inside the pool. And when they get out the pool, they notice they don't have short, stubby legs. They have big, long legs, things like this. But you get to see all kinds of cool, interesting optical effects. This is also what gives you mirages. For a mirage, what happens in that case is the air close to the ground is much hotter, so it has a different index of refraction of the air above it, which means that when the light is coming down, it actually gets bent in that case. So you're actually seeing things at different locations than what they actually are due to the fact that our eyes does weird things. So what your eye actually does is it ray traces things back to the origin of which it thinks it came from. Which means when you're looking at somebody in a pool with very short stubby legs, what's happening is the light is coming out, but then gets bent away from the normal because it's going from a high index refraction to a low index refraction. So your eye then ray traces it backwards to the origin of where it thinks it came from. So instead of coming from here, it appears as if it came from here. So in that case, that's what gives our eyes the illusion that the thing is actually shorter than what it is, because we're ray tracing the line backwards to where we think it came from. Our eyes don't understand bends and angles and things like this. It understands straight lines. That's it. So when I'm watching these things and it looks like this thing is bent, well, it's not bent. It's just that the light is bent and we're ray tracing it back to where we think it came from, even though that's not exactly the same location of where it actually came from. Okay with this? This happens a lot in other things too, like gravity. Have you ever heard of gravitational lenses before? You guys don't get out much, do you? Gravitational lensing is a nice, interesting thing. This happens by gravity as well. I'm going to write this here as a side note. But basically what will happen is if I had a planet here, and I'm sitting here, and say there's a star behind the planet, so here's my star, what will actually happen is the light being sent by the star will actually bend around the star, come to my eye here, be bent going in this direction, come to my eye here. And then what your eye does is it ray traces it backwards and thinks there's a star here, and ray traces it backwards and thinks there's a star here. What's up, Zach?
Like black holes, you can see all back of your head.
Exactly. Exactly. That's actually similar to a Poisson dots, but yes. So things like black holes, things like dark matter, things like stars, planets, galaxies, all these different things will actually cause this to happen. So here, you can actually think there are two different stars, but it's actually the same star. It just happened that the light bent around it due to gravity. Because as far as Einstein is concerned, which it turns out that's most of what reality tells us, is gravity is actually geometry. It is not a force. It's a manifestation of geometry, i.e. mass and energy and matter. Kind of off topic, but things like this happen all the time. So again, our eyes are stupid. We think we go always in straight lines. Nature bends, does all kinds of different things, which gives us these nice optical different effects. But anyways, as far as this kind of conversation is concerned, this is all we care about. Snell's law. So again, Snell's law says that the way this guy bends depends on the index refraction from the one to the other. If I go from a high index refraction to a low index refraction, it has to bend away from the normal. If I go from a low index refraction to a high index refraction, it has to bend towards the normal. There's another interesting thing about this as well, but let's do an example first. So, this one. Nope, we already did that one. So this says we have a swimmer has dropped her goggles to the bottom of a pool at the shallow end, which is only 1 meter deep. But the goggles don't look that deep. What is the apparent depth of the goggles? So let's draw our picture. So this is saying is here is my water. Here's the bottom of the water. Here are my goggles. And then here is my swimmer. My very skinny swimmer. And my swimmer is looking down at her goggles to see where they are. But again, what we know is that this depth here is simply equal to 1 meter. Okay? But she doesn't see them at 1 meter. She's going to see them at a slightly different location. So I want to know, what is the depth from the top of the water does she actually see her goggles at? So let's draw a few rays. So let's say this is a ray coming from the goggles. This is going to be our ray 1. So this is coming in at an angle of theta 1. It's then going to hit the surface of the water. Well, the index refraction of water, let's write that in here, and water is equal to 1.33, and that's going to an air, which is equal to simply 1. So here, since it's going from a high index refraction to a low index refraction, it has to bend away from the normal. So in this case, it's going to bend away and then go into her eyes here. So let's call this angle here then theta 2, where we know theta 2 is going to be greater than theta 1. Now again, what she's going to do though is she's going to ray trace this ray backwards. So I'm going to extend this guy back into here. which means that she's going to think her goggles are actually sitting here. So if she ray traces that ray backwards, she's going to think that this is the location at which that ray came from. So that this distance here, color I haven't used yet, red. So this distance here is going to be, it's called that H prime. That's going to be the apparent depth, and 1 meter is going to be the actual height of H. Seems okay? So far so good. So just to give us something, I'm going to call this distance from where the ray comes out to the center of the goggles as some distance of x. Just so we can keep track. And then this angle here is also theta 2. So this angle here from the blue one has to be the same as this angle here from the green one. Okay? So let's apply Snell's law. So Snell's law then says that what? N1, which in our case is N water, times sine of theta 1 must be equal to N2, but N2 is that of air, so that's simply 1 times sine of theta 2. Well, if I was dealing with sine, I would then have to know what? This distance, because this is a, let's see, do it this way. Yeah, so I'd have to know, according to this angle here, the opposite side, which is this distance, which I do know, but I'd also have to know the hypotenuse here, which I don't know. So here, let's make an assumption to make our lives a little easier. And let's say x is something much, much less than 1. Make it small. So as long as x is much, much less than 1, what that means then is if this was the only distance here, then this is going to be a very tiny angle, which means that, again, we can use the same thing we used in the previous problem, which is instead of using sine, we're going to use tangent instead. So I'm going to rewrite this then as NW tangent of theta 1 is then equal to tangent of theta 2. So again, as long as x is something very small, then both of these angles, theta 2 and theta 1, are also going to be small. Okay? So for theta 1, let's go ahead and use this triangle here. So this adjacent side here then is simply equal to the height h, and then the opposite side is then equal to the distance x. So remember, tangent is opposite over adjacent, so it's going to be NW x divided by h. And then for theta 2, I'm going to go ahead and use this triangle here, because this is theta 2. So here, the adjacent side now is h prime. The opposite side is now x. So this is going to be simply written as x divided by h prime. Those two x's are the same, so let's go ahead and cancel those guys out. And let's solve this guy for h prime. So I'm going to cross multiply here, or actually just invert both sides. That'd be fine as well. So if I invert both sides, what I get then is that h prime then is equal to h divided by n1. 1.33 is the same thing as what? 4/3. So n water is the same thing as 4/3. So this is 1 divided by 4/3, which is the same thing as 3/4. So this is 3/4 of a meter, which is then 0.75 meters. This is my optical depth. So again, when she ray traces this line backwards, she sees that her goggles are actually 0.75 or 3/4 of a meter down instead of the full meter down. Okay. Let's see if I have another example for you. That's 3. Let's go 4. Oh, that's thin film. That's the next topic. Everybody's doing okay? So before we move on to that, let me do something different. I gotta find it. I have a group assignment for you here, so now it's gotta find it. So you can't do the bottom one yet. We haven't talked about that yet. Let's just work on the top one. So the top one says a light beam strikes a 2 centimeter thick piece of plastic with a refractive index, that's the index of refraction, of 1.62. So that's this portion here, at an angle of 45 degrees. So that means this angle here is 45 degrees relative to the particle or the normal. So then it says the plastic is on top of a 3 centimeter thick piece of glass whose index of refraction is 1.47. So that's this part. It wants to know what is the distance d in the figure below where the light comes out from this configuration. So again, light is coming in here at an angle of 45 degrees. It's then going to be refracted, in this case, closer to the normal, because it's going from a low index of refraction to a high index of refraction. So that's going to make some distance, let's call that D1 here. Then it's going to go from N1 to N2, where N2 has a lower index of refraction, so it goes from a high to a low, which means it bends away from the normal. So it's going to bend away at another angle here, where then it's going to come out down here. So let's call the distance from here to here D2. So ultimately, what wants to know is what is the distance between where it entered to where it leaves, which is going to be this distance here plus this distance here. So overall, D is going to be equal to simply this distance plus this distance. Okay? So your job then is just to find that distance. So to do this, you'll just have to put on Snell's law twice. Okay? So first we got to go Snell's law across this boundary, and then Snell's law across this boundary to determine this angle and this angle. Once you know this angle and this angle, use then basic geometry to then find this distance. So you're just going to use tangent of this angle right here, geometry here, use tangent of this angle to find that distance, add those two distances. So, should be pretty quick. So I'll give you a little bit of time to do that. And then after that, I'll just show you some pretty pictures to talk about the next topic. But I don't think we're going to make it that far. We'll see what happens. I think I put this up on Blackboard. If not, just let me know. I'll put it up. Can't remember all the things I do. I don't even know what I ate for breakfast. Yes, it's coming from here. Yeah, so assume that the index of refraction above and below, you don't care about the below part, but above is 1. This is our last day in this room. So after this, by USI policy, we'll all be online after this. So. Degrees. Unless you want to. And if you're in radian mode, just make sure you switch back to degree mode, otherwise you'll get some weird numbers.
So not just do your.
Well, no, now you're going to use tangent. So tangent of theta 1 is equal to d1 divided by 2. Right. Solve for d1. And for the other one, if you call that theta 2, then. Yep, because that is 2 distance. I did. Also, Hanno's back out. Only took me 6 months to remember to bring it, but I found it. So yeah, okay, you gotta be back to your exams. There was an average. I don't remember quite what that average was. It was slightly better than the first exam. Definitely good. So it was on a positive trend. Yes. I remember right, the highest on the exam was a 95, I think.
I probably should have that.
All right, well, we only got like a minute, so I guess we'll call it a day. So have a great Thanksgiving, everyone. Do my best. Do my best. The good news is I have family coming, so they get to harass my children get to harass them instead of me. So that's the best part. I got a couple days break. All right, don't eat too much, don't drink too much, don't do any of those things too much.
Hey, Dr. Greenwood.
Okay. I'll add that up there later.